Modern lumber warps within months. Pressure-treated wood rots within decades. Engineered beams delaminate and fail. Medieval timber oak beams cut in 1200, installed in cathedral roofs, remain structurally sound after 800 years. The wood hasn't rotted, hasn't twisted, hasn't lost strength. Buildings standing since before gunpowder existed are held up by wood that modern foresters say is impossible. This is the story of a forestry and carpentry technology so sophisticated that dendrochronologists cannot fully explain how illiterate woodsmen selected trees that would outlast empires, and why every wooden structure you inhabit is designed to fail. Chapter 1. The beam that bows and breaks. Walk through any suburban development built in the last 20 years. Enter the attics. You'll see engineered lumber, laminated veneer lumber, I-joists, oriented strand board materials marketed as superior to solid wood. Now look closer. See the slight sagging in the I-joists, the delamination at beam connections, the compression crushing at bearing points. This deterioration isn't age. These houses are barely old enough to have teenagers. The engineered lumber is failing because it was never designed to last. The adhesives holding laminations together degrade under temperature cycling. The thin veneers crush under sustained load. The oriented strands separate when moisture penetrates the resin bonds. Structural engineers know this. Building codes acknowledge it by requiring more frequent inspection intervals for engineered lumber than solid wood. But engineered lumber is cheaper, lighter, and uses smaller, faster-growing trees. Economic efficiency trumps longevity. The average engineered wood I-joist has a design life of 30 to 50 years. After that, replacement is expected. Solid sawn lumber lasts 80 to 120 years. Neither approaches medieval timber's performance. Meanwhile, in the roof of Salisbury Cathedral completed 1,258 oak beams spanning 12 meters support the stone vaults. These beams are 766 years old. Structural surveys using ground-penetrating radar and resistance drilling show the heartwood retains 85–90% of its original strength. The beams could serve another 500 years. University of Oxford, dendrochronologists studying these timbers discovered something remarkable. The oak trees used were 200 to 400 years old when felled. They were cut from virgin forests of slow-growth timber that no longer exist. The growth rings are incredibly tight, sometimes 20 to 30 rings per centimeter. Modern oak grows 2 to 5 rings per centimeter. The density difference is profound. Medieval timber has specific gravity of 0.75 to 0.85. Modern oak is 0.6 to 0.7. The medieval wood is 20–30% denser, harder, and stronger than anything available today. But density alone doesn't explain the longevity. The selection process, cutting season, storage methods, and installation techniques all contributed to creating timber that modern forestry cannot replicate, even when using identical species. Chapter 2. The forest that grew slowly. Medieval timber came from ancient forests, old-growth stands that had never been cleared, where trees grew in dense competition for sunlight, producing straight trunks with minimal branching. These forests covered much of Europe until the 1600s, 1800s, when they were cleared for agriculture and urban expansion. The trees grew slowly because of competition and climate. In dense forest, only the tallest trees received full sunlight. This forced vertical growth energy went into height rather than diameter. The trees might take 300 years to reach harvestable size, but they grew strong and straight. The growth rate created tight-grain, narrow annual rings with high proportion of dense latewood. In fast growth conditions, trees produce wide rings with more earlywood lighter, softer material. Slow growth produces narrow rings, dominated by latewood dark, dense, strong material. The difference is visible. Medieval timber shows consistently narrow rings. Modern timber shows wide, variable rings. The old growth also meant trees had straight grain, the wood fibers ran parallel to the trunk axis. This provides maximum strength in bending. Modern plantation timber often has spiral grain fibers, twisted around the trunk, because fast-growing trees under ideal conditions develop this growth pattern. Spiral grain reduces strength by 20–40% and causes warping as the wood dries. Medieval carpenters understood this empirically. They tested timber by striking it with an axe and listening to the sound. Straight-grain timber produced a clear, ringing tone. Spiral-grain timber produced a dull thud. They could acoustically assess grain quality without seeing the internal structure. This knowledge allowed them to select superior timber while rejecting defective material. The Forestry Commission in Britain analyzed medieval timber from various structures, measuring ring width, density, grain angle, and knot frequency. The consistency was striking. Nearly all structural timber showed similar properties: tight rings, straight grain, minimal knots, high density. This wasn't luck, but deliberate selection from forests that naturally produced ideal timber. The forests are gone. Second growth and plantation forests grow faster, produce wider rings, develop spiral grain. Even if we let forests grow for 300 years, which economic forestry will never permit, they wouldn't replicate medieval conditions because the climate and forest ecology have changed. Chapter 3. The season that determines fate. Medieval foresters cut timber in winter, specifically in the weeks around the winter solstice, when the moon was waning. This wasn't superstition, but empirical observation of how cutting season affects wood durability. Trees are living organisms with seasonal cycles. In summer, they're actively growing, moving nutrients through sapwood, producing new cells. In winter, their dormant metabolic activity minimal, moisture content reduced. Stored nutrients concentrated in roots rather than trunk. Cutting in winter means lower moisture content, perhaps 40–60% versus 80–120% in summer. This reduces drying time and minimizes checking and warping as the timber seasons. It also means less sugar and starch in the sapwood, reducing the nutrients that wood-boring insects and fungi need to establish. The moon phase belief is harder to validate scientifically, but some research suggests correlation. Trees transport water through capillary action and osmotic pressure. These forces may be influenced by lunar gravity, the same force creating ocean tides. Cutting during waning moon, when gravitational pull is decreasing, might facilitate sap drainage. Whether the mechanism is real or the correlation is chance remains debated. What's undeniable is that medieval timber cut in winter shows superior durability to timber cut in other seasons. Studies at ETH Zurich compared decay resistance of oak timber cut in different seasons, using samples from dated construction. Winter-cut timber showed 40–60% less fungal colonization after 500+ years than summer-cut timber from the same period. The difference persisted across centuries. Modern forestry cuts timber year-round whenever market demand, weather conditions, and equipment availability align. Sawmills operate continuously, requiring steady supply. The economic logic prevents seasonal specialization. Some premium hardwood dealers still specify winter-cut timber, charging premiums for material that will perform better. But this is niche market, serving customers who value quality over cost. The medieval practice, waiting for winter, cutting only during specific weeks, is economically unviable in industrial forestry. Chapter 4. The drying that takes years. After felling, medieval timber wasn't rushed into use. It was stored sometimes for years, allowing slow, gradual drying that stabilized the wood without causing defects. The timber was stacked horizontally, with spaces between pieces, allowing air circulation. The stack was roofed to shed rain while remaining open to airflow. This created conditions for slow-drying moisture content, gradually declining over 2 to 5 years, from 40–60% at felling to 15–20% equilibrium with ambient humidity. The slow drying is critical. Wood shrinks as it dries, but the shrinkage is uneven, greater in tangential direction, along growth rings, than radial direction across growth rings. Rapid drying creates internal stress as the surface dries and shrinks while the interior remains wet. This stress causes checking, warping, and case hardening, where the surface is under compression and the interior is under tension. Slow drying allows the stress to dissipate gradually. The wood reaches equilibrium without developing defects. The timber is stable, straight, and ready for structural use. Modern kiln drying accelerates the process to weeks or days. Lumber is stacked in kilns with controlled temperature and humidity, forcing rapid moisture loss. This allows mills to turn inventory quickly. Trees can be processed from log to framing lumber in weeks rather than years. But kiln-dried lumber has residual stress that causes movement after installation. The wood continues adjusting to ambient humidity, warping and twisting as it equilibrates. Carpenters know this. They expect framing lumber to move and account for it in construction. Medieval timber, air-dried for years, didn't move after installation. The wood was stable because it had equilibrated before use. This stability is visible in medieval buildings. Timber beams remain straight after 600 years. Modern framing lumber visibly bows and twists within months. The Building Research Establishment in the UK conducted long-term studies comparing movement in kiln-dried versus air-dried structural timber. After 50 years, kiln-dried timber showed 3 to 5 times more warping and checking than air-dried timber. The rapid drying created permanent defects that slow drying avoided. The economic pressure for fast processing creates inferior products that require overbuilding and acceptance of movement that medieval construction didn't tolerate. Chapter 5. The joint that holds without nails. Medieval timber framing used joinery, precisely cut, interlocking connections rather than nails or metal fasteners. This wasn't primitive technology, but sophisticated carpentry, creating joints that strengthen under load and last centuries. The mortise and tenon rectangular hole receiving projecting tongue is fundamental. The tenon is cut on one beam, the mortise on another. When assembled, the joint is pinned with wooden pegs driven through holes offset between tenon and mortise. This offset creates compression as the peg draws the joint tight. The compression increases under load, making the joint stronger as the structure bears weight. Contrast this with nailed or bolted joints. Metal fasteners create stress concentrations at connection points. Wood compresses around the fastener, creating loose connections over time. Moisture fluctuations cause the wood to expand and contract around metal, further loosening the connection. Metal corrodes, especially in damp conditions, weakening the connection and staining the wood. Medieval joints avoided these problems. Wood-on-wood connections distributed stress over large surface areas. The joints could move slightly, accommodating wood movement without failing. As the timber aged and dried further, the joints actually tightened as shrinkage pulled them together. The joinery also encoded structural understanding. The timber framer knew where loads concentrated and designed joints accordingly. Heavily loaded connections used larger tenons, multiple pins, or supplementary joinery like pegs and wedges. Lightly loaded connections used simpler joinery. The joint complexity reflected the structural requirements. Modern engineered lumber uses metal connectors, joist hangers, structural screws, hurricane ties. These allow quick assembly by semi-skilled labor, but they create rigid connections that don't accommodate movement and introduce corrosion vulnerability. The medieval approach required skilled labor, but created connections that lasted. The Oxford Archaeology Unit examined timber joints from 13th century buildings during restoration. They found joints tight and functional after 700 years. Where joints had failed, it was from building movement or timber decay, not joint weakness. The properly made joints outlasted the structures they supported. Chapter 6. The oak that outlives nations. Oak, specifically European oak, Quercus robur, and Q. petrea, was the preferred timber for medieval structural work. This wasn't arbitrary, but recognition of properties that modern wood science has quantified. Oak's heartwood contains tannins, polyphenolic compounds that inhibit fungal growth and insect attack. These natural preservatives protect the wood from decay. The tannin content is high 5 to 10% by weight in oak versus 1 to 2% in pine. This makes oak naturally durable in conditions that would rot other species within years. Oak is strong in bending modulus of rupture around 100 megapascals for medieval tight-grained oak versus 60-80 megapascals for modern oak and 40-60 megapascals for most softwoods. The strength allows longer spans and more slender members, creating efficient structures using less material. Oak is stiff, high modulus of elasticity, meaning beams deflect less under load. This prevents the progressive deformation that causes structural problems in softer woods. Oak works well with tools. Despite its hardness, the grain is straight and splits cleanly. Medieval carpenters shaped oak with axes and adzes, creating smooth surfaces that machine planing hardly improves. But oak has drawback. It's slow-growing, taking 200+ years to reach timber size. Medieval forestry accepted this, managing forests for multi-generational harvest. They planted oaks their great-grandchildren would cut, creating continuous cycle. Modern forestry cannot accommodate 200-year rotations. The time value of money makes long-rotation timber economically impossible. Capital invested in trees that won't be harvested for 2 centuries produces negligible financial returns. So modern forestry uses fast-growing species, pine, fir, eucalyptus, with 20 to 40-year rotations. The timber is softer, weaker, and less durable, but the economic returns are acceptable. Some European forests still practice long-rotation oak silviculture, particularly in France and Germany, where state forest management thinks in centuries rather than decades. But these are exceptions, and even they use shorter rotations than medieval practice. The truly ancient oak timber, 300 to 400-year-old trees, producing the exceptional material medieval builders used, doesn't exist commercially. Remaining old growth is protected conservation land, not available for harvest. Chapter 7. The Carpenter Who Reads Trees. Medieval carpenters possessed deep knowledge of timber, recognizing by appearance how a tree grew, how the wood would behave, which pieces suited which purposes. This knowledge came from years working with wood, observing patterns, learning from successes and failures. The master carpenter could examine a log and determine growth rate by ring spacing, which side faced south by ring asymmetry, tension versus compression zones by color and density, spiral grain by bark patterns, internal defects by external signs. This assessment guided selection, which logs became beams, which became rafters, which became joists, which were rejected for structural use. The carpenter also understood orientation. A beam cut from the north side of a tree, where growth was slower and grain tighter, was placed where greatest strength was needed. A beam with visible compression wood, dense tissue formed on the underside of leaning trees, was oriented with compression wood at the bottom, matching its natural stress patterns. This orientation optimization used the tree's internal structure to maximum advantage. The wood was not generic material but specific piece, with properties determined by how it grew. Modern lumber is commodified. 2x, 6s are interchangeable, selected by grade rather than individual characteristics. This enables standardization and mass production, but eliminates the optimization medieval carpenters practiced. In timber framing revival movements, some contemporary carpenters are relearning these assessment skills. They report that the knowledge develops slowly initially. All logs look similar. But with experience, subtle indicators become obvious. The learning is experiential, requiring handling hundreds of pieces and observing how they perform. Books can describe what to look for, but recognition comes only through practice. This tacit knowledge is fragile. It exists in practitioners and transfers only through apprenticeship. When practitioners die without apprentices, the knowledge dies. We're experiencing this loss in real time as elderly carpenters trained in traditional methods retire without replacements. Chapter 8. The Failure of Modern Treatment. When modern lumber proved inadequate for outdoor applications, the industry developed pressure-treated wood, forcing chemical preservatives into the wood structure to prevent decay. This should have created durable lumber competitive with natural decay-resistant species. It failed. The first preservative, chromated copper arsenate, CCA, worked excellently, preventing decay and insect attack for 30 to 50 years. But it contained arsenic, creating toxic waste when disposed of and health concerns during use. CCA was banned for residential use in 2003. Replacement preservatives, alkaline copper, quaternary, ACQ, and copper azole are less effective. Treated lumber now shows decay after 15 to 25 years, especially in ground contact. Worse, the copper in these preservatives accelerates corrosion of metal fasteners, causing structural failures. Posts secured with treated lumber and steel brackets show bracket failure within 10 to 15 years. The most fundamental problem is that treatment is surface level. Preservatives penetrate sapwood, but not heartwood, which is denser and contains extractives that repel treatment. So treated lumber has protected exterior but untreated core. When the wood checks or is cut, the untreated interior is exposed, providing entry for decay organisms. Medieval oak's durability came from the heartwood. The tannins throughout the structure provided consistent protection. Modern treatment adds surface protection to inherently vulnerable sapwood. The protection is temporary and incomplete. Industry response has been developing ever more toxic preservative chemistries, each claiming superior performance. Each eventually shows problems: toxicity, corrosion, decay anyway. The fundamental approach, chemically treating inferior wood, cannot replicate the natural durability of properly selected species. Studies at Mississippi State University's Forest Products Laboratory compared decay resistance of treated southern pine versus untreated oak heartwood in ground contact. After 30 years, the treated pine showed 40–60% decay. The untreated oak heartwood showed 10–15% decay. The natural material outperformed the chemically treated material across decades. Medieval builders using oak didn't need chemical treatment. The wood was inherently durable. Modern builders using pine need treatment and accept that it will eventually fail. Chapter 9. The economics of replacement cycles. The construction lumber industry generates $60+ billion annually in North America alone. That revenue depends on wood being replaced, repairs, renovations, rebuilding. If structural lumber lasted 500 years, the replacement market would nearly vanish. This creates perverse economic incentives. Manufacturers profit from inferior products requiring frequent replacement. Better products reduce revenue. The economics are particularly clear in decking. Pressure-treated lumber decks last 15 to 25 years before requiring replacement. Composite decking lasts 25 to 40 years. Cedar or redwood, heartwood decks can last 40+ years with maintenance. True old-growth oak decking would last 100+ years. The homeowner's cost over 50 years. Pressure-treated requires 2 to 3 rebuilds, totaling $15,000, $30,000. Composite requires 1 to 2 rebuilds, totaling $12,000, $24,000. Cedar heartwood requires 1 rebuild, plus maintenance, totaling $10,000, $18,000. Oak heartwood requires only maintenance totaling $3,000, $6,000. The expensive, durable option is far cheaper across its lifetime. But economic systems don't encourage long-term thinking. Homeowners focus on initial cost, $3,000 for treated lumber versus $8,000 for oak. They choose the cheaper option, even though it's more expensive over time. The industry encourages this by promoting low-maintenance materials that ultimately fail faster than maintainable materials. Composite decking is marketed as maintenance-free, which appeals to time-constrained homeowners. But the composite cannot be refinished or repaired when it degrades. It's demolished and replaced. Wood decking requires maintenance, periodic cleaning and oiling, but can be sanded and refinished indefinitely. The maintenance-free option creates dependency on replacement. The maintainable option creates independence through repair. Medieval timber required maintenance. Medieval buildings show continuous repair throughout their lifespans, but the repairs extended life indefinitely. Modern building materials minimize initial maintenance while ensuring eventual replacement. We've optimized for short-term convenience at the cost of long-term economy. Chapter 10. The Craftsman Who Frames. In Vermont, a timber framer named Samuel Brooks practices traditional oak frame construction using hand tools and traditional joinery. He's 62, learned timber framing in the 1982 revival, when young craftspeople rediscovered the techniques from elderly carpenters and historical buildings. Samuel sources oak from local sawmills, The trees are 80 to 120 years old, not the 300-plus-year trees medieval framers used, but the best available. He air dries the lumber for 2 to 3 years before use, storing it in open sheds that protect from rain while allowing air circulation. The framing process is labor-intensive. Each timber must be marked and cut individually, scribing joint locations, sawing tenons and mortises, boring pinholes. The work takes 400 to 600 hours for a modest structure like a 6x8-meter barn frame. Industrial construction would complete the same building in 40 to 60 hours using modern lumber and metal connectors. But Samuel's frames will last 300-plus years with minimal maintenance. The industrial construction will require significant repairs within 50 years and rebuilding within 100 years. Over 300 years, the labor investment is comparable, but the traditional frame provides continuity, the same structure serving multiple generations. He charges $35,000, $50,000 for complete barn frames, prices that make many potential clients choose pole barns at $15,000. The economic comparison is deceptive. Samuel's frame lasts 300-plus years. The pole barn lasts 30 to 40 years. Over 300 years, 7 pole barns at $15,000 each total $105,000. The expensive traditional frame is half the cost. But the time horizon is beyond most people's decision-making. Samuel completes 2 to 3 major frames annually, supplementing with restoration work on historical timber frames. He's trained 4 apprentices who now practice independently. The knowledge is transferring, but the scale is tiny, perhaps 200 serious timber framers in North America, serving a market that could easily support 10,000 if economic thinking shifted toward multi-generational construction. The craft survives but doesn't thrive, maintained by individuals who value quality over efficiency and accept economic marginality in exchange for meaningful work. Chapter 11. The Science that Validates Antiquity. Modern wood science has extensively studied medieval timber, quantifying its properties and comparing them to contemporary wood. Research programs at forestry schools worldwide analyze historical beams, measuring density, strength, decay, resistance, and microstructure. The findings consistently validate traditional practices while revealing complexity that challenges replication. The USDA Forest Products Laboratory conducted comprehensive testing of medieval oak from dismantled structures. Their measurements showed density 25% higher than modern oak from the same regions, bending strength 35% higher, decay resistance 40–60% better, as measured by mass loss in standardized decay tests. The superior properties traced to 3 factors: slow growth, creating dense wood with high latewood proportion; old age before harvest, allowing heartwood development with high tannin content; and air drying versus kiln drying, preserving strength and dimensional stability. Attempts to replicate medieval timber using modern forestry have had limited success. Researchers can source slow-growth oak from old forests, air dry for years, and select winter-cut material. The resulting timber exceeds modern commercial oak but doesn't fully match medieval specimens. The difference appears to be environmental. Medieval forests grew under different climate conditions, in old-growth ecosystems that no longer exist, from genetic stock that may differ from modern populations. Some researchers are exploring ancient tree genetics. Oak trees can live 500-plus years. The oldest living oaks in Europe were saplings in medieval times. Comparing genetics of these ancient trees to modern plantation oak shows some differences. The old trees have allelic variants that are rare in modern populations. Whether these genetic differences affect wood properties remains uncertain, but they suggest that medieval timber came from genetically distinct populations. The implications are sobering. If environmental conditions and genetic stock have changed, we may be unable to produce timber matching medieval quality, even using identical techniques. The material itself may be irretrievable, lost along with the forests that produced it. Chapter 12. The Building that Adapts. Medieval timber buildings moved. The wooden frame flexed in wind, settled under load, adjusted to humidity changes. This movement was expected and accommodated through construction details. The joints were designed to allow slight rotation without failing. The frame could deform several centimeters without distress. Infill walls between timber posts were built to move independently, wattle and daub, or brick panels that could shift without cracking. This flexibility was strength. When earthquake or wind loading caused movement, the frame absorbed it through elastic deformation, then returned to position when loading ceased. Rigid construction would have fractured under the same forces. Modern construction is rigid. Steel, concrete, and nailed wood framing are designed to resist movement. This works excellently for designed loads, but fails catastrophically when overloaded. A medieval timber frame overloaded by storm would bow, perhaps permanently deform, but rarely collapse. The joints yielded before fracturing. A modern rigid frame overloaded by storm stays intact until sudden failure. The structure shows little distress, then collapses. This difference is visible in disaster response. After earthquakes, traditional timber frame buildings in Japan and Turkey often remain standing though damaged. Modern concrete buildings collapse completely. The flexible traditional construction degrades gracefully. The rigid modern construction fails catastrophically. Restoration architects working on medieval buildings report discovering the same pattern repeatedly. Buildings that have stood 500+ years show obvious deformation, leaning walls, sagging beams, out of square frames. Modern engineering analysis would predict collapse. Yet the buildings stand because they've accommodated movement incrementally across centuries. No single load exceeded capacity. The structure adapted, redistributed stress, and survived. This challenges modern engineering philosophy, which treats deformation as failure. Medieval builders accepted deformation as normal. The buildings were never perfectly rigid, but always functional. This pragmatism produced structures that outlasted more correctly engineered modern buildings. Chapter 13. The regulation that prohibits tradition. Modern building codes specify lumber grades, fastener schedules, and span tables, all based on modern keyline dried dimensional lumber and engineered wood products. Traditional timber framing doesn't fit these specifications. The timber is rough sawn, not dimensional. The joints are mortise and tenon, not nailed or bolted. The spans may exceed code allowances but use traditional precedent as justification. This creates approval challenges. Building inspectors trained on code provisions for modern materials may not know how to evaluate traditional framing. The structure might be superior to code requirements, but doesn't meet specific code prescriptions. Some jurisdictions require engineering stamps, professional engineer certification that the structure meets code intent. But engineers trained in modern materials may be uncomfortable approving traditional construction. The analysis methods don't directly apply. You cannot simply plug timber frame joints into standard connection calculators. Some regions have addressed this. Vermont has building code provisions specifically accommodating traditional timber framing, recognizing it as valid construction method with centuries of proven performance. Germany and France have standards for traditional fachwerk construction, allowing it without requiring modern equivalency calculations. But most jurisdictions require building department variances or appeals case-by-case approval that's time-consuming and outcome uncertain. This regulatory friction discourages traditional construction. Builders choose code-compliant modern framing to avoid permitting difficulties, even when they'd prefer traditional methods. The regulations aren't malicious, they're written for modern construction and applied universally. But universal application prohibits alternatives that don't conform to the assumed technology. Reform requires acknowledging that traditional construction is valid alternative, not inferior deviation. Performance-based codes that specify safety outcomes rather than specific materials and methods would accommodate traditional techniques while maintaining standards. Chapter 14. The forest that could return. Some foresters are attempting to recreate the conditions that produced medieval timber long-rotation forestry, focused on quality rather than quantity. These experiments are small-scale and long-term. The results won't be fully known for 50 to 100 years. The approach involves planting oak in dense stands, creating competition that forces vertical growth. The stands are thinned regularly, removing competitors while leaving the best trees to mature. Rotation length is 120 to 150 years longer than standard forestry, but shorter than the 300-plus years medieval trees grew. The economics are challenging. Land tied up in 150-year oak stands produces no revenue for a century and a half. The opportunity cost is enormous. Only landowners thinking dynastically, family forests passed through generations, can accept such long horizons. Some European aristocratic families continue managing forests their ancestors planted in the 1700s, 1800s, harvesting trees their great-great-grandfathers saw as saplings. These families operate outside conventional economic logic, valuing continuity and stewardship over financial optimization. State forests in some countries practice long-rotation forestry, particularly France's Office National des Forêts and Germany's state forest agencies. These institutions have multi-century perspectives and mandate public service over profit. They're planting oak today that will be harvested in 2150 to 2200, serving generations not yet born. Private commercial forestry cannot operate this way. The financial system requires 5 to 20-year investment returns. A 150-year rotation is incompatible with modern capital markets. So the commercial forest industry will never produce medieval-quality timber. It can only come from patient capital, family wealth, endowments, or state agencies willing to think in centuries. The experiments may validate that modern forestry could produce medieval-quality timber if we accepted long enough rotations. Or they may reveal that environmental changes prevent replicating historical conditions. Either way, the answer is generations away. Chapter 15. The Timber That Waits. You cannot buy medieval-quality oak timber. The trees don't exist commercially. The few old-growth stands remaining are protected, not available for harvest. The best available is modern oak, air-dried, from slow-growth trees 80 to 120 years old. It's better than standard kiln-dried lumber, but not comparable to true medieval timber. The lesson the timber teaches matters more than whether you can obtain it. That lesson is, organisms grown slowly, in natural conditions, with time to develop mature characteristics, provide better material than organisms forced to maturity rapidly in optimized conditions. This applies beyond forestry. Fast-growth agriculture produces food with lower nutrient density. Fast-growth livestock produces meat with different fatty acid profiles. Fast-growth humans pushed toward early achievement show different developmental patterns than those allowed to mature slowly. The acceleration optimizes for economic throughput but degrades quality. Medieval timber came from 300-year-old trees. It represented 300 years of accumulated growth, slowly building structure that would endure for 800 more years. Modern timber comes from 300-year-old trees, a 10x acceleration of production, and a 90% reduction in durability. We've traded permanence for efficiency. The timber that defies centuries is still there in cathedral roofs, barn frames, ancient buildings scattered across Europe and Britain. It's showing us what's possible when economic thinking extends beyond immediate returns, when quality matters more than quantity, when builders create for grandchildren they'll never meet. The wood is patient. It has stood for 800 years and will stand for 800 more, outlasting the modern structures built beside it, teaching anyone who examines it that the slowest, oldest, most carefully selected materials produce results that rapid, optimized, standardized production cannot match. The timber waits in ancient forests we'll never plant, in techniques we're forgetting, in buildings that refuse to fail despite our inability to replicate their construction. It's showing us that permanence requires patience, that quality requires time, and that the materials serving across civilizations are those allowed to mature naturally rather than forced to economic maturity. The question is whether we'll remember before the last old-growth timber rots and the last traditional carpenter dies, or whether we'll continue building with materials designed to fail, wondering why our structures don't last while medieval beams still hold up stones laid before nations existed.